All right, welcome everybody. I'm Scott Mora. It's a pleasure to have all of you here at the PATH seminar. So I'm delighted to introduce Professor Negar Mehr. Professor Negar Mehr is an assistant professor, in the Department of Mechanical Engineering here at UC Berkeley. Originally from Iran, got bachelor's at Sharif
Fancy.
University of Technology, came for graduate school actually here at UC Berkeley. PhD in mechanical engineering here actually, so you've returned back, but actually this seminar is very special for us because Negar Mehr is a PhD student, spent time in PATH doing research. And so it's great to have one of our own, but also just like very satisfying and exciting to see you graduate, go on, do amazing things, right? And then come back kind of like transformed in some way.
Yeah.
So Professor Mehr was a postdoc at Stanford, so spent time across the Bay, and then started as an assistant professor at UIUC, where they have an excellent university, a lot of expertise also in controls and game theory, which is something that Professor Mehr is really expert in, and then ended up coming back, runs a lab called Icon Lab. Are any of your students here?
No, actually,
on Zoom or
they're
anything?
all they're having a class now.
They're in class? Okay. Well, I love every word. I love hanging on every word of Professor Mehr, listening to her research and just life. So thank you so much for coming. We're delighted to hear about the research that excites you in this moment.
Thank you so much, Scott, for having me. The moment Scott sent me an email and invited me to give a talk, I was like, this is a very special talk because I remember all the times that I spent in PATH, essentially bothering all the researchers on PATH, struggling. It's like, what's a good research problem? What are the things which are solvable? And I think actually some of the audience in the Zoom, particularly Alex, I had all those kind of chats over coffee with him. Like, what does it mean to get a PhD? How can I make sure I do good research? So I kind of grew out of PATH, and people in PATH helped me essentially understand what it means to do research, what is good research, and ultimately get a PhD. And I had to go through all these institutions to convince Berkeley to hire me back because this place is just so special, and I'm so happy to be back. And I would love to essentially hear thoughts, questions, or feedback, so feel free to interrupt. I hope that this is kind of like we can have a conversation essentially in this talk. So I want to talk about some of the work that my group has been doing recently, which is focused on multi-agent interactions, many of which has applications, I believe, in transportation. And the principles and kind of the tools were among the ones that I learned throughout my PhD, but I kind of took them to a different level. So for those of us who work in controls, this is actually a very exciting time because you can just check out all these news headlines, a lot of excitement about how robots are going to change our lives, how autonomous systems are transform the way that we live. But among all these emerging applications, from autonomous cars that you see, maybe I can actually take a seat, in San Francisco, to drones delivering packages during COVID, all the way to space exploration. These are all very different robotic applications, but the key theme among all of them is that in all of them, we need robots to interact safely and intelligently with other agents. For example, autonomous cars, we see them in San Francisco. They essentially need to be capable of interacting with other autonomous cars or other human-driven cars. Robotic warehouse, many robots in Amazon warehouses essentially work together to accomplish a task, and many other examples of how you essentially need to have a robot go beyond cages around them and confined spaces in factories. However, these robotic interactions are really challenging, and that's why we actually don't have that many robots that can be integrated in environments that are shared with other agents. For example, here I'm just showing some examples of this, how the Amazon robot essentially hurt as human coworker, or kind of news headlines that I think many of us have seen unfortunate fatal crashes that autonomous cars had. I think the very extreme example, well, luckily it wasn't fatal, but the extreme example we saw recently is what happened with Cruise. So there are many of these, but these are not as specific to only human robot interactions. Even robots sharing the same environment with one another is challenging. So here I'm showing a video of Ocado's warehouse. Ocado is one of the biggest online grocery stores in the UK. And in this warehouse, which is designed and structured for the robots to operate safely and efficiently in it, even in such a structured environment, 3 robots collided with one another. The entire warehouse went on fire, and the share price of the company dropped significantly because of that, because people.
Do we have a video of the collision?
Of course not. But this is pretty recent. This is from 2023 that this happened. And I think I remember seeing the news, and I was like, oh, this is great. This is a good motivation for what I do. And I think what I do and what I've been focusing on is really all the different types of challenges that we need to tackle to essentially get around these issues and make sure that autonomous systems are capable of interactions with one another. More specifically, we work across 4 different domains. One is challenges associated with planning and control in these domains. What does it mean to do learning in these multi-agent interactions? What does it mean to have perception? And finally, the safety of these interactions. I probably won't get the chance and won't have the time to talk about all 4 of these. So I'll probably talk only about planning and learning, and then very briefly talk about the other 2 items. And if you had any questions, I would be more than happy to chat. So let's start with planning and control. And I want to essentially tell you why planning and control is hard in these problems. What makes it different from all the existing control problems that we probably even study in our classes, or what we studied during our PhD. And I want to motivate this by something that happened not long ago during the presidential campaigns. Here in San Francisco, the presidential candidate was essentially landing in, but because this autonomous car had blocked the intersection, the whole thing was delayed for 30 minutes, and someone had to manually essentially drive the Waymo car around to clear things up and so that things could go pretty smoothly. And this was because there were just too many humans around the Waymo car that it had no idea what to do. It was just too much for the Waymo car. Another example, which I can't really turn on the sound, unfortunately, because I think the Zoom won't take that, but it's quite fun, is the honking scenario with Waymo cars, which I think maybe you've heard about. So the thing is, I think many of you have heard about this, but this is a parking lot of Waymo cars, and they kept honking at each other like until 4 a.m. Where they kind of didn't know what to do and how to park, and all they could do was just honking at each other. It's actually quite fun. It's just watch this video later when you get a chance, because these people who are living near this parking lot are just being like, this is 4 a.m. and these are honking at each other, and people can't essentially sleep well. And then way more people had to essentially manually change some configurations in the code to avoid this behavior, which is essentially these cars being stuck around each other. So the kind of capability that robots lack as of now, which results in these behaviors that we see with the Waymo cars, for example, being stuck, is that the robots don't really have the capability to reason about the likely reactions of others to their own decisions over time. What does that mean? Think of this when we are trying to change our lanes. What we do is we kind of can predict that if I nudge in, the other vehicle may probably slow down and let me change my lane. So it's that reasoning capability that others could react to my decisions in this particular way, which we as humans have, and robots actually don't have that. So more precisely what we are looking at is to make sure robots have joint prediction and planning capability, meaning that when robots take an action, they can also keep in mind that, oh, the human is probably going to react in this particular way, so I better take another action. So really thinking about how others would react and account for that in their decision making. So that's a very high level capability that I'm hoping to equip robots with. But what does that mean mathematically? What does it mean for robots mathematically to have joint prediction and planning? And I'm going to explain this at a very abstract scheme. Let's say I have a bunch of agents, some of which could be robots, some of which could be humans. And each one of these agents has a task that they want to accomplish. Let's say each agent has a goal that they want to move to. And each agent is a dynamical system. They have a notion of a state and the notion of control, action, which essentially determines how their state evolves in time. And each agent has a cost function, very similar to our classical optimal control setting, where, for example, agent 1 wants to minimize the distance to its goal. However, the distinction here is that, for example, agent 1 also wants to make sure that it doesn't collide with agents 2 and 3. And if it collides, it incurs a high cost on agent 1. So what happens is that the cost that is perceived by agent 1 is not just a function of the state of agent 1 and itself, but also the state of others, because how close you get to other agents is dependent on where they are. So the problem is, in general, the cost that is perceived by every agent is not just a function of the state and actions of itself, but also the state and actions of other agents. So in other words, the cost functions are interdependent. Like what I do depends on what I see depends on what you do, and what you see depends on what I do. So I can't just be like, I optimize my own costs, because I can't. That depends on what the other agent does. And because of this coupling among the agent's perceived costs, we need to think about a solution concept. We can't just be like optimize the cost. And the solution concept that models the outcome of interaction in these settings is actually something which is very well studied in game theory. We are not the first to study this. Particularly, one of my reference books that I always go to is the Dynamic Non-Cooperative Game Theory book by Tamer Bashar from 1998. So the math principles have been there. And it turns out that if we have agents which are dynamical systems and they are interacting with each other, and each one of them has a cost and the costs are interdependent, then the outcome of the interaction, or the joint prediction and planning capability that I really wanted to achieve, can be modeled by Nash equilibria of the underlying interaction. And this Nash equilibrium concept really captures the joint prediction and planning capability that I was hoping to achieve for my robots. Mathematically speaking, Nash equilibrium is a solution in which no agent has any incentive for changing their behavior, meaning that at equilibrium, I'm doing the best that I can in response to what you're getting, and same thing is happening for you too. So all agents are happy in the sense that no agent is incentivized to change their decision. Kind of like an extension of optimality to multi-agent setting. And mathematically, what this means is that a set of control actions UI stars are equilibrium actions if for every agent I, the cost that is perceived by agent I by taking its equilibrium action UI star, then it fixes the actions of all the other agents, which I denote by U negative I, to be the equilibrium actions of others. Agent I is not going to benefit by changing its action from UI star to some other action UI. That is kind of encoding the fact that every agent is happy. Yes.
Sorry,
okay.
Really great so far. I am not a controls person, so please forgive me. I have a little bit more game theory. Is this like a perfect information game or imperfect information?
For now, it's a perfect.
Okay.
So you know a lot about game theory, that's first thing, and controls, and that's a great question. For now, I'm just looking at perfect information.
Okay, cool.
Great. So that's a solution concept that I'm going after, and you may be wondering, okay, so what? You were looking for joint prediction and planning. You're saying that an equilibrium gives me joint prediction and planning. So what is it that you're doing in your research? The problem is that although this solution concept is very powerful for capturing what we want, finding and computing Nash equilibria is actually really hard. Especially if you want to solve this on board a robot in real time, that becomes even more challenging. And the problem, which makes it really hard to find these Nash equilibria, is that finding Nash equilibria in this case is equivalent of solving a sort of coupled optimal control problem. This inequality has to be satisfied for every agent I. And for robotic systems, which are typically nonlinear dynamical systems, what we need to do is essentially solve a bunch of coupled nonlinear optimal control problems in real time, which is not that easy. And several recent works have looked into various assumptions to get around the computational tractability of finding equilibria. Some work has looked into assigning roles to agents. Some work has been looking at the hierarchy of dynamic models, but most of them can't scale beyond 2 agents, and even if they do, their dynamics that they can capture are very simple. So we were like, first, when I started working in this area, I was like, this is quite strange, because these equilibrium actions are actually very close to what we as humans do. They are a really good proxy for how we as humans behave. So I was wondering, what is it that makes us humans essentially be able to take actions which are close to equilibria, but computationally it makes it really hard for us to compute them on a robot. And I started to think that maybe actually there is some structure inherent in typical multi-agent interactions, which makes it easier to solve these equilibria. Maybe there is some structure there that we are not leveraging. And it turns out there is actually a structure, very simple structure there, which makes the analysis and the study of these interaction games much, much simpler. Particularly, what we found out was that these game theoretic interactions oftentimes become a very special class of games known as potential games. In our case, though, they are potential dynamic games. And for those of you who are in transportation, I think potential games is something you learn early on, and that's kind of how this whole thing was motivated. I was like, maybe potential games are actually applicable in this context. It turns out that actually potential games can help us a lot in terms of reasoning about these interactions and solving them. More specifically, in the context of dynamic game, potential games that we typically study in transportation are more of like a static games. But in this dynamic setting, what it means for the game to be a potential game is that we can find the equilibria of the game by just solving a single potential function P over the state and actions of all the agents. So instead of solving a bunch of coupled optimal control problems, what I can do is I can just solve a single optimal control problem, and that gives me the equilibria of my interaction. And what we did, this is what was like the first work in this line of work that we did. At the time, we were like, oh, interesting. It turns out that if agents treat each other symmetrically, then the interaction becomes an instance of a potential game. But I'm going to explain what this means, what the implications of this result are through a simple example. Let's say I have 3 agents, and I have the navigation task that each agent wants to move to a goal position while avoiding collisions with other agents. For example, agent 1 has a cost function J1, which is composed of a tracking cost, which I denote by C1TR. It is kind of like minimizing the distance to a goal, plus some collision avoidance costs, which capture the coupling among the agents. For example, C12A penalizing for collisions between agent 1 and 2. C13A penalizing for collisions between agents 1 and 3. Under such a cost structure, what we found out is that if agents treat each other symmetrically, game becomes a potential game. But what does that mean intuitively when I say agents treat each other symmetrically? What I mean by that is, let's say for agent 1 penalizes for collisions with agent 2 the same way that agent 2 penalizes for collisions with agent 1. If this property holds, then 1 and 2 are treating each other symmetrically. And if I have this property for all the other pairs of the agents, what I get is that my game is a potential game. And the potential function of the game is simply the sum of the tracking costs plus sum of the pairwise collision avoidances of the agents. And there's a simple navigation example. And it turns out that this simple setup that I showed through this example actually does a really good job in modeling driving and driving behaviors, interactive driving behaviors. So what this means is that all I need to do for to compute the equilibria of this game is minimize this potential function subject to the overall dynamics of the system. And now this is a single optimal control problem. I can use any existing trajectory optimizer to solve this. Any solution methods for optimal control problems would work. We picked the simplest one, something called iterative LQR. Essentially linearize the dynamics, have a quadratic approximation of the cost, solve LQR and repeat that. That's
One more, sorry,
Sure.
this is stretching me, so. You guys know, like Asimov's third three laws of robotics? Science fiction writer, like I had to double check, a robot may not injure a human being or through an action keep allow a human being to come on. Obviously, from the sci-fi side, but. Realistically, am I wrong in that? The payoffs are not symmetrical between a human and a robot, right? So we know that's an inaccurate assumption. I guess I'm just curious, but I'm guessing you're going to show that it actually doesn't matter.
Yes, exactly. Great, you can predict how this talk is going to evolve.
Is this finite time horizon?
Yeah, this is finite time horizon, yeah. So using iterative LQR, you can essentially have a behavior like this. Here I have two quadcopters. They want to swap their positions and they're running this potential minimization in a receding horizon fashion. And you can show that they exhibit this intuitive behaviors. They change altitude to avoid collisions with each other. But we were like, we don't like this symmetry assumption. It actually, maybe it's a strong assumption. How can we get around the asymmetries? It turns out we can also handle asymmetric interactions by looking at a kind of a larger class of potential games called weighted potential games, where there we can essentially have a weight on the collision avoidance term that couples agents, let's say 1 and 2. And we can formulate a weighted version of our potential function, and the analysis still holds. And we can get trajectories that look like this. Here you have an asymmetry in the cost functions. The yellow agent is kind of more conservative and it penalizes more for getting close to others, and you can see it deviates from that. So it gives you a way to account for these asymmetries.
And you can still solve the problem in a simple way. Okay.
Exactly. So we were like, great, this is great. How can we even generalize this? How can we go further with this? And that moment when I was thinking about going beyond this, I could hear Francesco Borelli's voice in my head, who could say, how about explicit hard constraints? It's like many of us use model predictive control and all these control algorithms because they can handle explicit hard constraints. And I was like, well, so far, everything that I talked about had no notion of constraints. How about constraints? Maybe collision avoidances, instead of being costs, they are actually hard constraints. You really want to avoid collisions, or maybe there are control actuation limits. Maybe there are equality constraints. So we started to look into how can we throw constraints into this. And it turns out that when we have constraints, we essentially need to find and look for a constrained version of Nash equilibria, where in the literature this is called generalized Nash equilibria. But all it is saying is that now, in addition to making sure that equilibrium conditions are satisfied, we also need to make sure that constraints are satisfied. But the nice thing is that same result still holds. We can show that constrained interactions could also become constrained potential interactions, which means that I can essentially find the equilibria of the game by solving a single constrained optimal control problem. So I need to stack all my constraints. Let's say G12 is the constraints between agent 1 and 2. G13 is the constraints between agent 1 and 3. And then I stack all these constraints with a vector called G bar of X. X is the state space of all the system. And that's it. Again, I have a single constrained optimal control problem. And with this, any constrained trajectory optimizer could work. We use Ultra, which is one of the fastest trajectory optimizers that can handle constraints. And here are the type of behaviors you get. For example, this is 4 agents in 2D trying to navigate, and you can see that they exhibit this intuitive trajectories and avoiding collisions with each other. We wanted to see how well we are doing compared to the state-of-the-art game solvers. So what we did was we looked at this setup, we generated 100 random initial conditions, measured the solve time of our method, and compared that with other game solvers that are out there. And here is the histogram of our solve time. It turns out with our method, which is the orange curve, on average, we are 20 times faster than the state of the art. And as you increase the number of agents, the savings from this reduction to potential games becomes more. And this is even with simple dynamics, with a more nonlinear, highly nonlinear dynamics, this actually gets even more.
So in theory, it would be better in, say, urban traffic environments with more interaction.
Exactly. Actually, way better, I think, because we have more agents there.
Yeah.
And thanks to this savings that is we can make in terms of the solve time, we can now run this in a receding horizon fashion on a quadcopter navigating around humans. And the humans are my students, obviously, but this is my favorite moment when the quadcopter and my student Anna was so scared of the quad, but the quadcopter was like take over, and then kind of like how we as humans behave. But the reason we were running this on a quad in the first place is that for these crazy flies, which are these small scale quadcopters, you have to run things really fast. Otherwise, it's among the different robots that I worked with, these crazy flies are the hardest to control. They're just so easy to essentially crash. But we could run this. This is a total of 19 states, so 19-dimensional system that we could run it in a receding horizon fashion quite fast. So this was very encouraging. But then I was like, here we have included collision avoidance as a hard constraint, but there is probably some more elegant use case for the fact that I can incorporate hard constraints into my interactions. So I was like, let's just go beyond inequality constraints and have equality constraints as well. Let's think of 2 robots that are carrying a rigid object, like a rod, around 2 humans in a room. So what this means is that I'm asking my robots to move this rod to a final position with a designated final orientation, while sharing the environment with some humans in that environment. This is really challenging because the robots need to think about how the humans would behave and how the humans will react, while making sure that they kind of maintain this equal distance from one another because they're carrying this rod together. So we're like, you have to reason about the interactions, you have to reason about collision avoidance, but you also have to reason about this equality constraint, that the distance between the 2 robots has to be equal to a fixed threshold, fixed distance. Part of the motivation for this experiment that we're hoping to run was actually a scene from Cinderella movie when I watched it as a kid. And my favorite moment was when these birds essentially helped Cinderella get ready. And every time I couldn't find my glasses at home, I was like, I wish I had these birds fly around, find my glasses, and then bring them to me. So I was like, can I have 2 robots fly around, find an object, and then essentially bring it to a final position? So that was kind of the inspiration behind this experiment that we ran. I haven't played the video yet, but let me explain the setup. There are 2 quadcopters here. They are connected to one another through a rod. And then, again, 2 other students in my lab, we have asked them to move from their start position to their goal position. We didn't tell them anything about the quads. We just told them that the quads want to transport this rod to their final position and orientation, which is designated by pink. And then we ran our algorithm in a receding horizon fashion. And here are the type of behaviors that we get. You can see that when agents get too close to each other, the quads can essentially intuitively change the orientation of the rod in real time to avoid collision. And then once the humans move, it essentially moves the rod to its final position and orientation. So it kind of, in my head, I was thinking, if two humans were transporting this rod, how would they behave around the other two humans? And it's quite intuitive. It's exhibiting a behavior which is very human-like in a sense. So that was, again, very encouraging for us. It was like, we were like, it essentially can reason about humans' behavior and its own coordination with other robots.
Can I ask a clarifying question, just because you've used the phrase, reason about human behavior a couple times. So a couple things clicked with me in this one, which is that, the human trajectories are not computed, of course, right? But they must have perfect information about the human state in that moment. you know?
Exactly,
And so you need to do receding horizon
Exactly.
rather than just one shot, because
exactly,
you need to correct for.
exactly.
But is there something more about? Is there some sort of like learning where they're trying to learn the dynamics of the human or predict it
Mhm.
somehow? Or is it just, looking at their current state? Yeah, how is it modeling the future evolution of the human
That's a
state?
great question. So the thing which I kind of hidden throughout the first part of the talk is that I assume that the robot knows the human objective.
Mhm.
The robot kind of knows what is it that the human is trying to optimize.
Oh, so it's giving them a model
Exactly. So the model is.
inaccurate, because.
Yeah, exactly. And that's why I need to run it in a receding horizon fashion. But the robot, knowing the human's objective, can sort of predict that, oh, for someone with this objective, this is probably what they're gonna do. And that's why it can, the reasoning that I mentioned that the robot reasons about human behavior is that the robot knows that the human is going to act selfishly, just cares about optimizing that objective function, which I assume the robot knows. And then that helps it predict how the human behaves. But there are two challenges with that. First of all, in the first place, how does the robot know what objective the human is optimizing?
Yeah.
And second, the human's objective may change, right? So you have to have another component to kind of be like, oh, I'm essentially moving to somewhere and then I forgot my coffee and then I go back. So my objective all of a sudden changes. This still doesn't have that component, which is dynamic re-identification of objectives. But I talk about how we can learn humans' objective maybe in a couple of slides.
Okay,
It's a
Thank
good
you.
question.
thank you.
So we were like, amazing, what else can we do? It turns out that because of this structure that we leverage, which is the reduction to a potential function minimization, we can use all the tools from control on distributed optimization, distributed optimal control, distributed model predictive control. If you have multiple robots, you can distribute the computation of this potential minimization among them, and you can make this even more scalable. But we wanted to look into other interaction domains, going beyond navigation. We were looking at behaviors like drone racing, which is actually quite fun to watch. So it takes some time to watch these.
Fast.
They're too fast, but it's so elegant. And I don't know, this is with human pilots. I have no idea how humans manage to control these in such a fast and complicated behavior. And these behaviors like this. One drone pushes the other to the boundary to the point that it can't control, the human can't control the drone and it crashes, it's out of the game. So they kind of know strategically pushing each other's to the boundary so that the drone crashes and is out of the game. But these are super, super complicated behaviors and it's really hard. I have no idea. These people spend so much time on training to essentially control these drones. But we're like, to some extent have some hope for having autonomous racing of agents against one another. Let's say two drones race against each other. Our setup is not as complicated as the ones you saw in human piloted drone racing. But we're just like, if I have a racetrack, simple, and I want to have a couple of drones, you could think of them as cars or really any autonomous system, can I have them race against each other? And it turns out you can essentially cast racing as another instance of a potential game. And what we did was we designed this simple experiment where we had this race track. And the drones started, but our ego agent, which is the green agent, started the second, started the first. There are many trials of this video. And the first one, the ego agent, ours started first, but it has a lower speed limit than the other agents. And other agents are just using reactive NPCs. And you see that our green ego agent kind of pushes the blue agent, overtakes, and then it manages to win the game, although it has a lower speed limit. So the blue agent can have higher acceleration, but it can't win the game. The other setup that we tried, the second trial, was when our ego agent using our algorithm, started the second, but it has a higher speed limit. And again, here you see that it kind of blocks the blue agent again, overtakes, wins the race. And kind of we can see that our ego agent starts to leverage the fact that others also want to avoid collisions to kind of overtake or block and manage to win the game. But these are all very kind of encouraging examples of how these game theoretic models would work. However, I just want to briefly talk about something which happens, which is the existence of multiple equilibria. I didn't touch that. This actually whole thing started when I went to CDC in Singapore 2 years ago. And I was just constantly bumping to people on my first day. And it took me a day to realize that, oh, here the convention is yield to the left to avoid collisions, whereas in the US it's yield to the right.
Goddamn Brits.
So I was like, well, technically, these are two equilibria, both of which are valid. It's just that we have a social norm and convention to pick one over the other. So this could be one valid equilibrium, or it could be the other. Both of them are valid as long as the two agents agree on which equilibrium they pick. The problem is going to be when the two commit to different equilibria and they crash. So it's really the need to account for the existence of multiple Nash equilibria and identify the equilibrium which is compatible with the convention or the social norm that is picked in the environment. And it turns out that we can actually account for these. We can look at different minimizers of the potential function, and that gives us different sorts of equilibria. For example, the equilibria that we get are here, there are 6 different equilibria. The setup is that two agents want to swap their positions, but there is this large obstacle, which is the gray circle. And agents only get to see each other or the obstacle when they're closer than a certain threshold to one another. And first, when we were looking at this, I thought, oh, there are only 4 equilibria. But it turns out there are actually 6 equilibria, because maybe, for example, both of them go to the top, and then all of a sudden now they have to avoid collisions and coordinate with one another. But the nice thing is that by finding different local minimizers of the potential function, you can identify all these equilibria and be like, oh, which one is the one that people in this community typically pick? But I want to briefly talk about learning in multi-agent domains, because that's a really important piece, which Scott, I think, pointed to, and it's actually quite challenging. And like I said, everything that I talked about so far is valid and makes sense as long as the robot knows the objective function of every other agent. And one could argue, how do we know humans' objective function? If you ask me what my objective function is when I'm driving my car, I don't know. I can just be like, I can drive my car, but I don't know what objective I'm optimizing. And even when you're designing a robot, you're like, how do I know what objective should I design? Because it's not always actually that easy to design an objective function for a robot. You have a question?
I guess I'm curious, especially thinking on the AV side and getting to the weighted cost functions. How would you accommodate for somebody basically assuming, oh, I know that the vehicle will do everything in its power, including getting into a collision itself with an inanimate object, to avoid hitting me, which is a
Mhm.
concern and fear that that's how some people will approach automated vehicles, where it's like, oh, I'm not going to, even if it has plenty of space, I'm not like going to ignore the AV and I will never let it merge because
Mhm.
the AV will do everything it's powered to.
Exactly.
Yeah.
And I think that really goes back to my hypothesis is that humans' objective will change dependent on what agent they're interacting with,
Yeah.
right? When I'm kind of surrounded by human-driven cars, I probably have one objective, but in San Francisco, when there are way more cars around me, I probably
And
have a different objective.
What I'm thinking of, this is a famous example of the early Waymo vehicles kept on getting rear-ended around
Yeah,
Palo Alto, right?
exactly.
Do you guys know that story? It- Basically, they were super risk averse. So at every single stoplight, stop sign, they came to a full and complete stop, and they waited for all the other vehicles to come to a stop before going ahead. Now, for those of us who've driven a car in California, that's not how people actually drive. So they were trying to be super risk averse and actually caused an increase in
Yeah.
collisions because they kept on getting rear-ended.
Yeah.
Probably would have changed over time once people
Yeah.
saw that they were acting that
Exactly.
way, but other folks were assuming that these Waymo vehicles would act like a normal
Exactly.
California car and go through, and they kept on
Yeah,
rear-ending.
exactly. And I actually wanna, I'll go back
Sorry.
to this point, no, but I think that's a really important one. And I want to talk about how this problem has been studied in the literature and what is missing from how this is studied in the literature. So the problem of kind of cost modeling, cost inference, cost learning is not new. People have looked into this problem in the reinforcement learning literature extensively, where the idea is, let's look at how a human or an expert in a task accomplishes that task, collect a bunch of trajectories of how they did that task. And under the assumption that the human is noisily optimizing a cost function, we try to learn the cost function, or kind of like, let's identify the cost function under which these trajectories would have been the optimal trajectories. That's kind of how inverse reinforcement learning works. And it works based on a principle called like maximum entropy. It doesn't really matter, but the idea is the probability of taking an action by the human is proportional to the exponential of the expected reward that is associated with that action. However, the problem with this inverse reinforcement learning literature is that it's all focused on essentially you're learning from an agent that is acting in isolation. You try to model and learn humans' objective when the human is just driving on its own and is not surrounded by anyone else. Whereas in many real world tasks, like driving particularly, driving is so interactive. And to learn humans' objective, what these works do is that they're like, okay, if I want to learn the objective of this merging car, then I treat all the other cars as some obstacles that I want to avoid and try to learn the objective of that merging vehicle. But I want to advocate that that is actually not the right way to model humans. The example that I give is that if a student wants to work with me and they want to be like, let's see what type of advisor Negar is or how she interacts with her student. If she watches me, he or she watches me when I'm sitting in my office doing work on my own, that doesn't reveal anything about how I interact. But if they want to learn about how I interact with my students, they better watch me when I'm interacting with other students. So I want to argue that to really learn how people interact with others, you'd better watch their interactions. You can't just be like, look at them in isolation. So you essentially what you want to do is let's say how does we have a bunch of humans that are interacting with each other, and from that we want to infer how they're treating each other. How can we learn their cost function? And what this means is that the interdependencies of cost functions that we started with, we now have to account for that, not just in the planning, but also in the cost learning phase. And I want to argue that instead of learning from demonstrations of just one agent, we'd better learn from demonstrations of multiple agents interacting with each other. And in the interest of time, I'm going to skip the details of, mathematically how we modeled this and what goes into the details of this. But I just want to show you some results using real world data of merging, which is what I've been using to motivate this. So this is from the interaction data set, which was actually created here at Berkeley by Professor Tomizuka. And this is a highway in China. I want to essentially be able to predict the merging behavior of the drivers. And we collected a bunch of trajectories, about 80 trajectories of vehicles trying to merge. And we divided this data into a training data set and a test data set. We use a training data set to learn the cost functions of these cars interacting with each other from our data, and use that in our test data set to predict the accuracy of how well we can predict vehicles' motion, and compared that with single agent IRL, which is what people typically use, and IDM, intelligent driver model. I assume all this audience knows, but we kind of optimized all the parameters of IDMs. IDM was kind of like the best that we could do, which is very tailored to driving, whereas our setup was just very agnostic to the choice of the application domain. And you can see that our method, which is the blue curve, is way more accurate than the state-of-the-art single agent IRL, very close to IDM. And when you look at the trajectory prediction over time for longer horizons, it actually gets better than IDM. So this was very encouraging, and we were like, let's test this on another domain. So what we did was we actually worked with some colleagues at UT Austin. We collected trajectories of students and pedestrians on campus. We essentially had these cameras and then LiDARs and recorded these trajectories. And we were like, let's see if we can better predict humans' motion by this multi-agent IRL method that we have been developing. And the same story holds here too. The blue curve is ours, and I'm plotting the position kind of accuracy in prediction, the error in prediction over time step. And you can see that the blue curve, which is our method, is doing a way better job in predicting how the other pedestrians are going to move. And it's better than behavioral cloning and hybrid methods between behavioral cloning and inverse reinforcement learning, and also better than single agent IRL. So the key takeaway message for me was that you'd better watch how agents interact with each other. And this goes back to your point that to learn how humans behave around an autonomous car, you better watch those interactions and learn from that, as opposed to two humans. So I have so much else to discuss, but I'm going to skip that. I just want to give you some insight that we've also been, so far I talked about multi-agent inverse reinforcement learning, but even forward RL is quite challenging, quite hard. Credit assignment is quite a challenge there, but we have some interesting results there too. One last thing that I want to mention is that perception, and I think this is going to have some implications for transportation. As you may know, perception is a key bottleneck when it comes to real-world robotic systems. But what we have been showing is how multiple autonomous cars or multiple robots can essentially fuse their 3D reconstruction of a scene to reach a much better representation of an environment. For example, on the first row, you see what happens with what we have, the perception systems that we currently have. On the bottom row, you see what happens if multiple agents kind of share their 3D reconstruction of an environment with one another. We have been testing it in hardware, showing that very realistically, these robots don't get to have continuous communication with one another. Only 5% of the times they get to communicate with each other. The left robot perceives just the left half of the room. The right robot just senses the right half of the room. But yet both of them collectively manage to build a 3D representation of the entire room, which I think is going to be very relevant to AVs. Safety, we've been looking into risk sensitivity, how robots can be risk sensitive in their interactions, reason about the risks and take actions that minimize their risks. And we show that the more risk averse the robot becomes, yielding behavior emerges. Some interesting behaviors are present there too, but I want to pause here because I've been covering so much. I got to present the work that all my students were doing, so it would have been impossible without them. So thank you all for your attention, and happy to answer any questions you may have.
That's amazing.
Thank you,
Negar.
Scott. Thank you. Thanks, everyone. Yes.
For the distributed IRL, is it just predicting the cost based on the current state, or does it take into account like several previous states.
So it assumes that you have collected a bunch of full trajectories of how agents interacting with each other. So you kind of use that data offline and then learn these approaches. But then, kind of related to what I mentioned to Scott, you need to have like another layer on top of that, be like, you can refine your model of how humans behave online as you're interacting with. So this was more of like a prior. I learned this prior. My prior is better than other priors, but still, I think you will need some sort of a Bayesian update on this to adapt to the human that you're interacting with. There any questions over chat, or we're good?
I don't number chat
I
yet.
didn't see anyone I
Okay.
last checked.
Okay.
Maybe, I'll
This
have
was,
to,
and I just, so this is
yeah.
outstanding, thank you so much.
Thank you.
It's really great to see you back here.
Thank you.
I had a question, what was interesting about like holding the rod
Mhm,
and moving
mhm.
around. It occurs to me that, is it possible to get into a bad situation where they're not accounting for the rod in the middle and can sort of like hit a human in the middle?
Yeah.
Like, how do you deal with
Yeah.
that?
So the challenge is that you can never kind of guard against all sorts of crazy things that humans could do. So these work well as long as humans are reasonably well behaved. Um, Typically what we saw is that the two robots are kind of frozen. They kind of like, oh, we have to maintain our equality constraint. And if the human just tries to get too close to them, they're like, okay, I don't try to move forward. We even get to see sometimes they move backwards to some extent. But if the human is doing, because the robot is like, human is rational to human is behaving rationally to some extent, and if the human becomes just too irrational, or the objective function that the robot has in mind about the human is not accurate, then yes, that can happen, which I think kind of explains that this need another additional layer, which is how much should I trust my model of the human? Because if I don't have a lot of confidence in what I think the human would do, I better be really cautious. But yes, those could happen because the human has the authority to do anything they want.
Alex, did you have something? I see you were unmuted online.
Yes, I appeared. First of all, Negar, welcome back to Berkeley.
Good to
and-
see you, Alex.
Likewise. And second, I wanted to ask you a little bit about how does the feedback work, with what frequency, and or you are using kind of piecewise planning control?
Yeah, so that's a great question, Alex. We are running this in a receding horizon fashion with a 20 hertz frequency. So the horizon, I think, is maybe 10 time steps. So we kind of look at this finite horizon game, solve them, implement the action, and then move forward. But typically it's around 20 hertz for these applications that we had. And the feedback that it gets is the current state of all the agents, not just the robot, but also the humans, which is like, I want to know currently where the robot is and where the other humans or the other robots in the environment are.
And when you compute the Nash equilibrium, so you compute how many, so you compute so many steps ahead, or how does this work?
Yes, this is like a dynamic game. So it essentially predicts the trajectory that results under Nash equilibria, very much like NPC, where you predict the actions for the horizon, but you just use the first one. It's just the same thing too. You predict the trajectories of all the agents in robot's head, obviously. And then you apply the first control input and then move on.
And does this Nash equilibrium has this optimality, optimality principle, when you compute the Nash equilibrium for the longer horizon, and then if you move along the trajectory, or pieces are also Nash equilibria?
That's a great question, Alex. And I think the reason you're asking that is because in dynamic games, there is a distinction between Nash equilibrium and sub-game perfect Nash equilibria, which is the challenge is that in these dynamic games, even if the game is deterministic, A Nash equilibrium and trajectory level may not satisfy this principle of optimality, like perfect sub-game Nash equilibria.
Mhm.
And that's actually a bottleneck in these multi-agent games. But with these potential games, what I showed is at the trajectory level, we are achieving Nash equilibria. And it turns out that for these classes of games, it is very close to being sub-game perfect equilibria
I see.
because the dynamics are separable, and then the coupling only happens through the cost functions. But we have been looking into that for quite a while, and the type of result that we have so far is that it's approximately satisfying optimality conditions in that sense.
Uh-huh. Thank you.
Thank you, Alex.
Where can we find more information about your qualitative perception work?
I can send you the link to the papers.
Yay.
Just shoot me an email, I'll share the references with you.
I have one last question, if that's okay. So on your final point that we need more information for learning on interactions between humans and robots, especially let's say with AVs. How the heck is that going to happen? Because there is currently a massive amount of data on human machine interactions, but it is entirely privately owned and they are not going to share it.
Yeah, exactly. So the reason why I actually picked cost learning over what industry uses, which is just predict humans policy, is that this is way more data efficient than, let's say, what Waymo uses. They just have this huge amounts of data and train this behavior prediction model, generative models, which can predict how the humans behave. But what we have seen is that with these methods, we trained ours with like 80 trajectories. So it's not too much to essentially ask for. And the cool thing is that this acts as a prior for you. So I oftentimes think about how we as humans drive. I'm driving on the freeway and I see someone is just too fast and like, oh, I better watch out. This person is out of my normal expectation of how humans behave. And I think you can capture all of that on top of this layer that we have been developing. This is way more data efficient because I'm putting so much structure into robots' reasoning that the human is trying to optimize an objective function, and the objective, the more information you can provide about what you think the objective is going to look like, the less data you have. Whereas Waymo is like, I don't care about the objective. I just want to have like a policy generative model which predicts humans' motion distribution. And for that, I don't think we can afford to do that because we don't have that much data available.
Well, like, so for example, where I was going with that is, you know, like, how do you see this work interacting with the Waymos of the world? Perhaps say, not even forgetting the systems developed, but from a regulatory perspective, because that is a really, really big concern. How do we appropriately regulate these AVs? And
and I think for regulation, I was actually looking at some news kind of pieces on what does it take to regulate AVs. And I think this goes back to the safety part, which I didn't really get to discuss much. But I think to think about regulating AVs, let's say here I have two instances where robot is navigating around some agents and their motion is uncertain. I think to regulate AVs, you need to somehow quantify the risk that is taken by the AVs. And we can't get around it. You want to be like, you can never guarantee that an AV is going to be 100% safe. But can you guarantee that the AV is always willing to take actions which maintains its risk, the risk that is taking below a certain threshold? So the safety discussion, I think, is going to really matter for regulating AVs. And in the two parts that I discussed, I didn't really say.
No, I'm just, this game may be too deep. I'm just throwing it out there. But like, for example, since you feel like your system, you don't have all the data that you have, though it is more efficient, I'd be curious if everyone is scared of setting up official rules for any sort of regulation of AVs, because then they'll just follow the rules and they'll obviously be safe according to those rules. If you had real life trajectories, I'd be curious, for example, a subset, like a random sample of Waymo trajectories. Could you compare what the Waymo vehicles did to what your hypothetical system did there? And would that be an alternate way to at a
I
low
see, I
cost,
see what you're saying.
regulate the AVs and identify if they are operating in a safe or a safe enough.
I see,
fashion.
yes, so.
Not, that's not sufficient for everything, but that would be
I see,
one
I see.
data, yes.
So that's a great, actually a great thing to do, that if someone gives me a lot of data of how AVs operated, I can run it into these models and kind of be like how human-like they were.
Yeah.
How safe they were, because are they actually safer than humans? And it really goes back to how they interacted with the humans. You can't just be like AV drove on its own for this number of miles. That's just
No.
not a good metric. But be like, identify these settings and be like, how two humans interacting with each other, how an AV and human interacting with each other, how far are they from each other, or what objective the AV is implicitly optimizing, how is it different from different types of humans?
The reason, by the way, I'm asking this for some practical purposes. So Scott and I and some others will be at AV in the City Symposium on Friday. Also there, Scott, I want to make sure I introduce you to her, is one of my friends who was in the USDOT, and she recently moved to Google to be in charge of like selling public data,
Right, yeah.
data sales for public. So this might be something that she would be
Yeah,
interested
I mean,
in as well. Yeah.
obviously, the more data that we have from how these AVs have operated, the more you can tell about how they're operating. Because right now, typically our data sets are in the form of data collected from humans.
Yes,
Right?
which
We
is,
don't really have that much
Yeah.
data from AVs. And I've been trying so hard. When I was here and when I started at Illinois, I tried so hard to connect with these companies and get their data. No, it didn't work out. Yeah.
All right, guys, this has
We're
been
over.
fantastic. For those that have stuck it out this long,
Sorry,
thank
guys.
you.
I got excited.
Thank you, everyone.
Yeah, thank you.
Thank you, Scott, for having me. This was lovely to be back at Path. I love this audience. This is where I grew.
Oh,